Introduction to Capacitive Sensing, Part 2, CSA and CSD CapSense. Welcome to the Introduction to Capacitive Sensing training module. In the course, we will be introducing CSA and CSD capacitive sensing. Both of the capacitive sensing methods that we will be covering in this module use switched capacitor networks at the input stage. In order to understand each method, we must first understand the basics of switched capacitors. The essence of the switched capacitor is the use of capacitors and analog switches to perform the same function as a resistor. So why not just use a resistor? There are two distinct advantages to using the switched capacitor network. First, when using CMOS design technology, the network on the left actually takes much less area than the resistor on the right. Also, you can see that the network on the left contains two switches with frequencies phi 1 and phi 2 labeled on top. By modulating the frequencies of these switches, we can actually alter the equivalent resistance. In other words, the switched capacitor network is a tunable resistor. This is an example of a timing diagram for phi 1 and phi 2. If you look closely at the shaded bars, you will notice there is a slight break between when each switch is closed. This is because, by design, both switches are never closed at the same time. But how does the network on the left equate to the network on the right? Let's prove that this works. In order to derive an equation which relates capacitance and switching frequency to resistance, we start with three known equations: I equals C times dV over dt, F equals 1 over delta T, and R equals V over I. Rearranging I equals C times dV over dt by solving for V produces delta V equals I times delta T over C. Substituting this equation in for the V in Ohm's law, we get an equation which includes resistance. Simplifying this new equation, we get a formula for R that reads R equals 1 over F times C, where R is the equivalent resistance of the circuit, F is the switching frequency, and C is the capacitor being switched. In order to better understand this formula, we will now run through an example. A typical sensor capacitor is around 20 picofarads, and in this case the pulse width for phi 1 and phi 2 are each 5 microseconds. We can plug these values into our new formula and arrive at an equivalent resistance of 500 kilo ohms. Going back to why capacitive sensing is used in the first place, we can begin to see what a capacitive sensing solution will need to have. At the most basic level, a solution needs to be able to detect the difference between the presence and absence of a conductive element such as a finger. In order to do so, the sensor capacitance, or Cx, must be continuously measured. This measurement will need to be digitized into a format that can be calculated, and finally decisions can be made depending on this digital data. So, how do you measure the sensor capacitance? So now that we know how switched capacitors work, how is that used to create the capacitive sensing solutions mentioned earlier? Let's first take a look at CapSense successive approximation, better known as CSA, and then at CapSense sigma delta, or CSD. Here is a block diagram for CapSense successive approximation, also known as CSA. It consists of a programmable current source, called the IDAC, which is attached to a bus connected to a switched capacitor network to ground. The switched capacitor network is formed by Cx, the sensor capacitance, and switches phi 1 and phi 2. The switched capacitor network charges an external modification capacitor known as CMOD. The voltage on CMOD is routed through a low-pass filter into a comparator, where it is compared to a reference voltage. The output of the comparator feeds a counter clocked by an oscillator. The output of the counter is used for data processing, where the status of the sensor is determined. In order to understand CSA, it is helpful to look at the waveforms during a single scan of a single sensor when there is no finger present. Here we see the voltage on CMOD with no finger present. We can divide this waveform into three regions. The red area is region 1. During this phase, the initialization occurs. The switched capacitors initialize CMOD to a starting voltage referred to as V start. Once that is done, we move to region 2, the green area. This is the scanning region. In region 2, the bus is charged by the IDAC current source until CMOD equals the reference voltage Vref. Then we move to region 3, the blue region. The scan is completed during this region, and the voltage on the bus returns to normal and post-processing occurs. Let's see that again from the block diagram level. As mentioned earlier, CX is part of a switched capacitor network, so as we walk through the three regions, we can substitute in the equivalent resistance, RCX, for the switched capacitor network. This helps simplify the circuit. As we have just went over, in region 1, the voltage on CMOD settles to a value we have referred to as V start. But what is V start? V start is a voltage value across RCX or CMOD that is just below Vref. We need to find an IDAC current source value that will allow the voltage on CMOD to settle at this value V start. The name CSA comes from the method used to find this golden IDAC current value, which is through successive approximation. This is done once for each sensor when the CSA Sensing Method is first started. At that point, the golden IDAC value is stored and reused on later scans. So at the end of region 1, the voltage across CMOD is at V start. Next, this voltage is passed through the low-pass filter and fed into the comparator, which compares it to Vref. The output of the comparator feeds the counter, which counts how long it takes for that voltage across CMOD to cross that Vref threshold. Finally, during region 3, the scanning is completed. Data processing is performed on the output of the counter and compared to a baseline. This comparison determines the status of a button, or in the case of a slider or touchpad, the location of the centroid. During this time, that steady-state baseline is also updated. The baseline is dynamic, which helps the sensing method account for environmental condition changes like temperature and humidity. So how does this differ when there is a finger present? Remember, we saw before that the equivalent resistance is equal to 1 over F times Cx. If we substitute this into Ohm's law, solving for V start, we see that V start equals 1 over F times Cx times IDAC. The only thing that changes in this equation is Cx. So we can see that the larger the value Cx is, the smaller V start is. When a finger or other conductive object is within proximity of the sensor capacitance, Cx, is increased. An increase in the sensor capacitance decreases the equivalent resistance of the switched capacitor input stage. A lower resistance translates into a lower starting voltage. Remember, CMOD is in parallel with Cx, so the voltage across the equivalent resistance is equal to the voltage across CMOD. Since the starting voltage is lower when there is a finger present, it takes longer to reach the comparator threshold. The time that it takes to reach the comparator threshold is measured in counts of the oscillator, and these counts are compared to the baseline set earlier with no finger present. This is how CSA is able to tell the difference between the presence or absence of a conductive element. Here is a summary of CSA. Increase in Cx reduces RCX, lowering the starting voltage V start. Lower starting voltage causes longer charge time. Longer charge time enables the counter for a longer time. Due to the counter's longer enable time, higher raw counts are measured. Comparator triggers when VStart is equal to VREF, stopping the counter. The raw counts are processed by firmware, such as updating the baseline, comparing the measurement to the baseline, and then determining button status versus centroid location. Now here is the block diagram for CapSense Sigma Delta, also known as CSD. This method includes a switched capacitor input stage containing the sensor capacitor CX. The switched capacitor network is between VDD and the voltage at CMOD. The switching frequencies are controlled by a pseudo-random sequence generator. CMOD is a fixed external modification capacitor that we will continuously charge and discharge. There is a bleed resistor, RB, which drains charge off the modification capacitor CMOD. The voltage on CMOD is compared to a reference voltage. The output of the comparator is fed into a synchronization latch, which is clocked at half the speed of the comparator. The output of this latch controls the bleed resistor switch. When the comparator trips, the bleed resistor switch will close, discharging CMOD until a new value is stored in the synchronization latch. The output of the synchronization latch, also referred to as the bit stream, is AND'd with the PWM and enables a counter. The output of the counter is used for data processing, where the status of the sensor is determined. In order to simplify the circuit, the switched capacitor input stage has been replaced with its equivalent resistance, RCX. Notice that RCX charges CMOD. Again, a greater capacitance at the sensor means a lower equivalent resistance, allowing more current to charge CMOD. The current through RCX charges CMOD until the voltage reaches the reference voltage VREF. At that point, the comparator will trip. Once the comparator trips, the bleed resistor is connected to ground. The bleed resistor will allow CMOD to discharge until the voltage drops below VREF. Once the voltage across CMOD falls below the VREF, the comparator goes low and disconnects the bleed resistor. So if we look at the voltage across CMOD versus the output of the comparator will oscillate at a certain frequency and duty cycle. The output of the comparator is fed into a bit stream filter. All the filter does is break the bit stream into measurement windows, then pass the signal into a counter for the measurement. Signals with a higher duty cycle will enable the counter for a longer period of time and thus have a higher counter value. Key points to remember from the CSD sensing method are that an increase in sensor capacitance causes a decrease in equivalent resistance. A decrease in equivalent resistance means more current charges the modification capacitor. More current charging the modification capacitor results in it faster charging. A faster charge time leads to an increase in the duty cycle. Summarizing the CSD sensing method. Increasing the sensor capacitor, CX, reduces the equivalent resistance, RCX. A lower equivalent resistance allows more current to charge the modification capacitor, CMOD. More current causes CMOD to charge at a faster rate. A faster charge time increases the duty cycle. Larger duty cycles keep the counter enabled for longer periods of time. Due to the counter's longer enable time, higher raw counts are measured. The raw counts are processed by firmware. Just like in CSA, we update the dynamic baseline and then compare the process data to the baseline. This comparison determines the status of a button, or in the case of a slider or touchpad, the location of the centroid.